Okay, good morning. So today we'll continue with the previous lecture yesterday, where basically I talked about this work that we did with Daniel, Tomsky, Lekulaevsky, and Maxime Monsovoy. In the previous lecture, I talked about some interesting charge effects that appear in multi-insulators, and I focused maybe for the pedagogical reasons in a triangle, basically in a single triangle. I have a model in a molecule of 3 sides. And what I plan to do today is indeed, I'm going to couple these trimers. Right? You can think of these trimers as molecules, and see what happens when you start coupling these objects. Of course, when you couple them, you will get some interesting many-body physics. But in particular, during the during
It's not selected. If you click on it once, it will work or not. Sorry about that. So basically, yesterday I was saying that one motivation for studying these charge effects in multi-insulators is that it provides you with a very simple framework for understanding how spin ordering can induce charge ordering. So yesterday, you will see it today again in an actual model. In particular, for a subset of charge orderings correspond of ferroelectric states, so charge orderings in which you get an electric dipole moment, and I will explain that today as well with a very simple example. How can you get photoelectricity induced by a magnetic field, as soon as you couple these triangles? And in particular, we also saw yesterday that there is another subset of spin orderings that are basically so-called associated with scalar spin chirality, where you have emerging orbital electric currents, right? Similar to the ones that are discussed in the context, for instance, of ITC, but for metals here they appear already in the insulating state, in the multi-insulating. So we saw yesterday that this effective charge density operator basically is proportional to a bond operator, right? Meaning that a necessary condition for getting a charge density wave induced by spin ordering is to have bond ordering, right? So the bonds that originally were equivalent in your system have to become spontaneously inequivalent. For the case of the current, as I was saying before, the effective current operator is proportional to this triple product between the 3 spins, the so-called scalar spin chirality. So again, this is the order parameter that you need in order to get spontaneous orbital currents, right? And something that I would like to mention today that I didn't mention yesterday is that you can have exotic situations in which the mean value of S is equal to 0, so you don't have the conventional magnetic order, but still the mean value of this object is non-zero. And if you want to detect it, then you will have to measure this orbital current and corresponding orbital magnetic moments produced by that. Right? And there are some examples, some compounds where people speculate you may have this kind of situation. So I also explained yesterday that if you now, I was saying that to get some charge distribution, bond ordering is a necessary condition. Now, if you consider this molecule, right, the simplest way of making the bonds inequivalent is, to consider this particular ground state of the Heisenberg Hamiltonian on three sides, where you have a singlet, right, between sides 2 and 3, and then an ampere spin in side 1, right? And what we saw is basically that for this kind of space, there is a net electric dipole moment pointing along this vertical direction that, from this reference frame is the x direction. And that happens basically because there is some electronic charge transfer from sides 2 and 3 to 1. Right? There is a fraction of your electron that goes from here to here. So finally, there are these two components of the polarization. There is this orbital current, and what we saw yesterday is that if we renormalize conveniently these three operators, Px, Py, and the orbital current operator, then we obtain these pseudo-spin variables, very similar to the ones that Jerome was discussing in the previous lecture, right, that correspond to orbital degrees of freedom, as we will see in a moment, and close to algebra, as Jerome showed in the previous lecture, right? The big difference between these three variables and the previous ones is that now, instead of having a quadrupolar electric moment associated with this orbital degree of freedom, actually what we have is an electric dipole moment associated with the x and the y components, and then an orbital current associated with the z component. Right? But from the formal point of view, the mathematical point of view, we will see that we get the same type of Hamiltonians that we were showing in the previous lecture. The only difference is the order parameters, physical order parameters of these orbital components. So finally, what we also saw in the previous lecture is that if we consider this single triangle, right, and we do this low energy projection of the coupling expansion of the additional Taubman model, we get a Heisenberg interaction between nearest neighbors, and basically, since in a single triangle, this is you have interaction of everyone against everyone, this can be written as a total spin square, meaning that you have two doublets, with three spins, total spin can be 3/2 or 1/2. There are two doublets, right, which are the ground states according to this expression. And then there is a coordinate, spin 3/2 coordinate that will be the excited state. And the gap between these two manifolds is 3j over 2, right? In particular, we chose, if we choose this basis, right, for describing this doublet, this is a basis of states that have a well-defined, the following quantum numbers, a well-defined tau z, so the eigenstates of the current operator, tau z can be plus or minus 1/2, that is the meaning of this plus minus. And then Sz can be plus minus 1/2, right? Again, because so basically with these quantum numbers, these two quantum numbers, we can fully characterize these four ground states. So as I promised, now today what we will do is basically we will consider now an array of these molecules, right? These triangles. These are the red primers. This is one of these. What I was considering before. And let's say that now you couple them, right? This is not just my imagination. I mean, I was talking to Yasu Takano 1 month ago, and he was showing me different organic compounds that correspond to this situation, where you have molecules, right, trimers, which are weakly coupled, and indeed they form another triangular lattice. You can see that these triangles form another triangular lattice. The reason why I'm not mentioning the compounds is because the data is kind of secret, and they didn't want me to tell what the compound is, but there are organic compounds that are in this situation. And by the end of the talk, I will show one trimer compound. So, anyway, the story is that now you can see that these trimers form a triangular lattice, right? And these three vectors, E1, E2, and E3, that will play the role of the X, Y, and Z directions that John was describing in his talk, and now they correspond to these three unitary, these three vectors correspond to the three principal directions in this triangular lattice. They connect nearest neighbor triangles, right? And you have this one along the X direction, and then E2 and E3.
So the leads are not equivalent?
Sorry?
So the leads are not equivalent?
Some?
The leads, because you say the nearest neighbor triangle.
Yeah, there are also these nearest neighbor triangles, but you see that here the interaction goes from one vertex here to two vertices here, but here it goes from 2 to 1. So basically, this Hamiltonian, I will write the Hamiltonian by adding, on every single triangle. So every single triangle will be denoted with this index R, right? And then, I count interaction, I have 3 interactions to nearest neighbor. So this interaction will be counted when I'm sitting on this triangle. Right?
So basically, you see all the objects, right?
Right. Right. So this Hamiltonian indeed is running over this, vector R. There is a label for each of the triangles, right? And then this internal index J is, 1, 2, and 3 at the 3 sides of each triangle, right? So basically, this is the intra-trimer interaction. This is the term that we were analyzing previously. But now we have an exchange interaction, J prime, between trimers of the same layer, right? Right. That's the reason why these relative vectors E1, E2, and E3 appear in this term. And I will also assume that we have a stacked triangular lattice. So basically, we have chains. Each of these sides correspond to a chain in this direction, and then there is an interaction J double prime along the chain. So this is the axis that is perpendicular to this. And finally, I would think that there is also, we would assume that there is an external magnetic field that the corresponding Zeeman gapping to the magneticity to the spin, and we are choosing the quantization axis for, parallel to the magnetic field. Okay, so now, we will follow a procedure similar to the one that we followed to derive the for deriving the Heisenberg Hamiltonian from the Howard Hamiltonian. Why? Well, basically because, if you consider each unit here, right, if we start from the situation in which, J prime and J double prime are equal to 0, right, you have a very, tiny degeneracy, right, which is basically 4 to the number of trimers that we have in this line, right? Because on each one we have 4 different grams. So if now we, as I mentioned before, to describe this internal degrees of freedom, these 4 states of each triangle, we will need now not only the spin, right? Not only the total spin that can be plus or minus 1 half, but there are 2 doublets, so we cannot distinguish. Since there are 2 doublets, we cannot distinguish them only with the spin operator. Then we will need also these effective pseudo-spin or orbital operators, right? And again, we are associated with, the X and Y components are associated with the X and Y components of the polarization, and then the Z component is associated with current density operator. Okay, so what we have to do basically is, use the standard recipe of degenerate perturbation theory. Essentially, what we need to do is now to project the perturbation, that is basically these 2 terms, into this low energy subspace generated by these states, right? So on each triangle we have this set of 4 states, right? And the low energy subspace is basically the tensor product of all the triangles or all the triangles of this local subspace. Sorry?
So when you contrast with the surrounded by different, and the bonds are different directions, right?
Right, yes, so, yes.
So here the sites are fixed, right?
Yes, here the sites are fixed and all the triangles are vertical, so I'm thinking that, the one that you have on the top is 1, then, 2, and 3.
Yeah, but when you say this will be diagonal, you have to change the face.
No, well, that will appear, that face that you have in mind will appear in a moment, when we project, the Hamilton. And for the moment, we only have isomer interactions on bonds, right? On the red bonds, we have J. On the black bonds, we have J prime. And then on the bonds along these chains, we have J prime. So these faces will appear once we project, basically, the Hamiltonian into the lowest energy subspace that I was saying is generated by these states. So once you perform this,
what is state 0?
Sorry?
What is the state 0 in the first equation at the end? That's next slide.
Next slide.
And the equation, state 0 at the end.
At the end?
Vacuum state, right?
The
vacuum.
0. Yeah,
What is this? Vacuum. This is the vacuum. Right?
So how do you define the vacuum state?
Basically, if you have it will be the trimer without any electron. So now we are creating 3 electrons, 1 in each side. Which is basically what at Calvin you have modern insulator, so essentially you have 1 electron on each side. Okay. So this is the empty state. Okay, so now basically to project, what we have to do is, to get the Hamiltonian projected into the lowest energy subspace, basically we need to project these operators, these spin operators. Right? And once you project these spin operators, remember that this index J is the internal index of each trimer, can be 1, 2, or 3, then we get this expression. This is now the total spin operator on each triangle, right? But, it's multiplied by this operator now that contains the pseudo spin, and you can see here the analogy with the previous lecture. You see that you get the inner product of the pseudo spin, right, times nj, where nj is basically the unit vector, the normalized ej, right? So ej is basically these 3 vectors. Okay, so here we can see that there is a correlation now between the spin that we are considering on the single triangle, trimer, and basically the direction, the bond that connects the center with that corner of the triangle. So now the only thing we need to do once we know this is we have to replace this expression here in the Hamiltonian to get this low energy effective Hamiltonian, right? And once we do that, indeed, we get Coulomb-like Hamiltonian, right? The difference here is that I didn't start with I didn't have a multi-orbital model to start with. This orbital physics, spin orbital physics now is emerging from a single orbital model, precisely because we have this kind of decorated lattice. We have molecules that are completely coupled, and because of fluctuation, because of this additional orbital free. So, and you can see that now we have, again, this S.S interaction, that is SE2 invariant, because the original model is SE2 invariant. And then the interaction, the effective interaction that we get between these orbital degrees of freedom is anisotropic, as Jerome was pointing out. In general, that should be the case. That should reflect the discrete symmetry of the triangular lattice. And this is, again, a compass-like model because when you consider the interaction between 2 orbital degrees of freedom along a given bond, along a given direction E sub L, basically it's only the component parallel to that direction that's interacting with each other, right? That's the reason why these models are called compass-like. Okay, so now in order to analyze, this Hamiltonian better, let's consider particularly, let's assume for the moment that the intralayer interaction is 0, G prime is equal to 0. So we only get this interaction, along the chains. Something interesting.
Red triangle are on top of red triangle.
Yeah, top red triangle on top of
Because
red.
then maybe actually
Yeah, exactly.
triangle
Yeah.
is,
This is not like FCC or HCC.
AAA.
AAA, exactly. Right, and precisely because it is AAA, you see that, interestingly enough, the interaction that you have here, right, when the intralayer interaction is compass-like, the interlayer interaction is UR invariant, it's XY line.
You calculate this.
Yeah, right. The triangles, the sides are one on top of each other. AAA.
No, but they all come to the equation, right? So
Sorry?
they all come to the equation, right? Because the
Yes, they all couple.
it's different symmetry, right? If we shift for example.
Yeah, you have C3 symmetry, but C3, this type of interaction is enough to guarantee that you want. So, yeah, it's not common to have continuous symmetries with orbital models, but sometimes they appear, right, at least at some level of approximation. And so now, if we assume that J prime is equal to 0 for a moment, then we get essentially a model for this, this is this ladder of triangles stacked one on top of each other. And we get a very simple model indeed, right? And just to simplify the model even more and understand what is the physics, let's assume that the magnetic field is high enough to fully polarize these magnetic moments. Let's say that we are applying an external field that is very high, right? And we manage to fully polarize these fields. So in that case, we can replace this S.S operator by 1/4, right? Because S.S is identically equal to 1/4 if we have a fully polarized field state. And we end up with an extremely simple Hamiltonian that is just an XY model in one dimension, right? And this model can be solved exactly, essentially because it can be mapped into a Taiwan or spinless fermions in 1D. Right? I will not go through the details of that mapping. It's not necessarily, it's not the point of this lecture, but that's the way you can solve this model exactly. And then what you know also is that that model is critical. Basically, you have gapless fermions. And the critical fluctuations, the fluctuations that dominate and become, make the section critical equals 0 correspond to ferroelectric fluctuations if this J double prime is negative. In other words, if J double prime is a ferromagnetic interaction. And I would assume from now on that this J double prime interaction indeed is ferromagnetic. Okay, so essentially what you can get, what you get from this very simple limit, is that your dielectric constant is associated with the 2-point Fourier transform of the 2-point correlator of the tau x, or tau y, right? Because these are essentially x and y component of the polarization, diverges as 1/t to the 3 halves, right, when the temperature goes to 0. So we have critical ferroelectric fluctuations, and now the next question is what happens when we couple these chains or these triangular ladders, when we make J double prime different from 0. So now we have to go back to this effective Hamiltonian that I derived originally. We have to put back this term. Right? And again, let me assume that the magnetic field is very high, right? High enough to fully polarize the magnetic moments. So now what you get is now, in addition to this XY orbital interaction that I just analyzed along the Z direction, we have this compass-like interaction in the XY plane. And now you can see that the J prime, the intralayer interaction, is antiferromagnetic, positive, right? Then again, this interaction between orbital degrees of freedom is ferro. Right? So let me assume also that J prime is antiferromagnetic, it's positive, right? And let's propose a simple, impedance that corresponds to a 3 sublattice structure. So first of all, since these interactions only involve the x and y components of the pseudospin, it makes sense to propose a solution in which the mean value of tau z is equal to 0. And now, and for the x and y components, we will assume that we have a 3 sublattice solution. That means that we will divide our triangular lattice of trimers in 3 sublattices that are this red, blue, and green here, and we will let the phase, right, the orientation of these dipoles, to be in principle different for A, B, and C. So this these are these variables phi and L, right? Where L can be AB or so. And now we will minimize the energy as a function of these three variables. For that, the only thing we need to do is to replace the operators by their mean value, right? We will get the energy per site as a function of this variation of variables phi A, G, and C.
So, just a quick question before
Sure.
we continue. What happened to these terms linear and tau?
That's a very good question. Yes, sorry. What happens is that they cancel because the linear in tau, as you pointed out, right? Sorry, yeah, that's a good point. But once this is uniform, right? S of S is replaced by 1/4 because the spins are fully polarized. Then I have to sum over L, right? And essentially, what I use is that the sum of tau of for each side we have 3, the sum of NL over 1, 2, and 3, right? And the sum of these 3 vectors is equal to 0, right? The sum of N1 plus N plus N3 is equal to 0. So right, they disappear when this becomes 0.
I mean, a simple question. So, but what's the Hilbert space? I mean, you see, the spins, they don't commute with curves, right? It's not a spin.
They do.
Ah, they do.
Right, right. Yeah, that's another good point. The orbital and the spin degrees of freedom commute with each other. Right?
So, but then by the high fields, you mean the fields which don't break this singlet or the bonds? Because if you say polarized derivative, right?
Oh no, you're right. You're absolutely right. I'm also, yeah. When I say yes, it's another very good question. I'm not fully polarizing the spins to the extent that I'm exciting, these spins to the high energy quarter, to the 3 halves. Here we are working at low energies, so we already got rid of the 3 halves. So high field means a field that is still much lower than this gap, right? That was 3J over 2. But high compared to J prime and J double prime, so it's high enough to fully polarize the spin 1/2 gametes that we have in each plane. Is that clear for everyone? Right? So because I did, I reduced the Hamiltonian to the lowest energy subspace, right? But of course, Leonid is right. If you apply a huge field, then eventually you will start, exciting each traveler into the 3 halves state. Right? But again, here the assumption is that the field is much lower than the gap, right? Than J, basically 3 halves of J, but much bigger than J prime and J double. Okay. So now, as I was saying, if we minimize the energy, so basically if we write out the energy per site as a function of these 3 phases, right, A, B, and C, you get this simple expression. It's clear that if J prime is positive, it's antiphotogrammetric, as I was assuming, then it's clear that the ground state configuration corresponds to all these phi L being equal. And as John was mentioning, they are equal to phi. So in principle, they can take any value, right? And that is what he was mentioning by the end of his lecture, that although we had a compass model with a discrete C3 symmetry, at the classical level, right, you want degeneracy, right? So the ground state solution for these electric dipoles is ferroelectric indeed, and they can be pointing, the electric dipole moments can be pointing in any direction. And as Sharon also said, this degeneracy is removed when you include the quantum fluctuations. And how do you include the quantum fluctuations? Well, the easiest way is to do some linear, apply some linear spin wave approximation, but now not to spins, but to electric dipole moments. And essentially what you do, this is described in the textbooks, so I will not spend too much time, but essentially what you do is simply you choose now your quantization axis along the moment, right, the orbital moment, and then you apply a linearized constant Primakov transformation, right, to map these spins 1/2, so spins 1/2 of the bosons, right, and essentially you obtain an expression now for this tau x, tau y, and tau in general in any direction as a bilinear in bosons. Basically, there are also cubic and higher corrections in these bosons. That's the reason why here I put approximated. But the whole idea of this linear spin wave approach is to keep only the terms that are quadratic in the bosons. Right? It's like a small, we are basically performing small oscillations around this solution of equilibrium. So that's the reason why I can cut this expansion and then get rid of the cubic terms. So now the only thing you need to do is, okay, replace again the operators by these expressions in the Hamiltonian, and you get the so-called spin wave Hamiltonian, which you can see is quadratic in the Holstein-Primakov bosons. And to diagonalize this Hamiltonian, you exploit the translational invariance of these systems. So of course, it is convenient to introduce these new bosons in Fourier space, right, and rewrite the Hamiltonian. And once you do that, then you get a much simpler expression, right, where you have the usual normal terms, the bosonic dispersion, plus the normal. And this quadratic Hamiltonian, as far as you know, can be diagonalized with a simple Bogoliubov transformation, right? New going to new bosonic operators, where the coefficients, basically Q and PQ, are given by this expression bonds and so much important. So by doing that, you end up with this diagonal form of the spin wave Hamiltonian, right? And what you find out is that the dispersion relation is given by this simple expression. And interestingly enough, if you take the long wavelength limit, if you assume that the wave vector is very long, sorry, it's very small, the wavelength is very long, you get that the dispersion relation goes to 0, right? Linearly in the absolute value of Q. And this, I would say, pseudo-Goldstone mode, right, is produced indeed by this U1 degeneracy, right, that you had at the mean field level. Right? Of course, here you can see that this U1 symmetry of the solution will be broken by the quantum corrections, because already in this Hamiltonian we can see that the ground state has a correction that is sum over Q of omega Q over 2 divided by is of Q over 2. And you can see that omega Q here already depends on phi. Right? So if you compute this, the quantum correction to this ground state energy, now you will see that actually the best solutions correspond to these electric dipole moments pointing along the principal directions. Right? It's still a ferroelectric solution, but they have to point along the directions 1, 2, or 3, or basically the rotation of those 3 by C.
No, okay, then, in principle you have also solution with Z is non-zero. So you have chosen only this dipole solution because of the perpendicular coupling.
No, because there is no coupling for tau Z. I mean, so tau Z
I mean, just
doesn't.
in plane there is one.
Sorry?
Perpendicular to the planes. In chains you have only X.
No, right, but
That's why you have chosen this solution.
right, but the perpendicular to the plane also gives you interaction that involves, it gives you an XY-like interaction.
Yeah, that's why we.
That's why I'm
you
choosing
chosen this solution.
planar focus. Yeah.
Now, can you explain actually why perpendicular really only XY and not VB? Not tau Z, tau Z?
You mean why
Why
only?
perpendicular only XY form? Is it possible to explain for it actually? Why does it contain tau Z, tau Z?
Right. Let me think for a couple of minutes. Finish, and I will try to answer that question. But yeah, I think basically, it has to do with the fact that to project. Sorry. Yeah, tau Z is a current, right? So to get interaction. So yeah, let me think a little bit. I will go back to the section. So anyway, so the point is that so now I did everything for a high magnetic field. Let me assume the question that you can ask. So we just saw that for a very high magnetic field we have a fully polarized spin state with a ferroelectric configuration, right? That is the lowest energy state. Now what happens if we lower the magnetic field? And if we lower the magnetic field again, we can try with a mean field solution, right? But the important thing to keep in mind is that when you lower the magnetic field, now these spins, right, typically on a triangular lattice will form a 120-degree structure, right? They will be like this. And in the magnetic field, one will start counting the spins. So this product S dot S will change sign. Right? So if we are starting from the fully polarized situation, S dot S is positive, of course. But once you start opening this umbrella because you are lowering the magnetic field, eventually this will change sign. And if this changes sign, right, the effective coupling between your orbit and degrees of freedom also changes sign. So what you expect indeed is to have a transition from a ferroelectric state to an anti-ferroelectric state, right? Because the sign of the effective coupling between orbitals is changing. And indeed, that's what you get, at least at the mean field level, and you get it via a spin flop transition, right? Since the interaction between the moments also is modified by the orbitals, basically what you get is that the spins flop from the fully polarized configuration to a configuration in which they form this canted 120-degree structure. But simultaneously, you have a discontinuous transition from a ferroelectric to this 120-degree structure, where you have electric dipole moments pointing around these three different directions in the three cell lattices. One can compute, this spin flop field, right? That is given by, you see, is determined by J prime, because J prime is the only antiferromagnetic interaction. Remember that J level prime is ferromagnetic, right? And this shows you in a very simple realization, how these magnetoelectric effects work and how can you get a multiferroid behavior. Basically, you can switch on the uniform electric polarization by applying a magnetic field. And you can also see how this orbital physics basically emerges just from simple exchange interactions, right? Magnetic interactions. So finally, to understand, why. So you may be asking, why do you get, ferroelectricity for high enough fields? So it's illustrated probably to try to go back to the original spin language, right? And see what a ferroelectric state along the x direction means. And what it means, if you remember on the previous slides of yesterday and also today, it means that you have on every single triangle, you have a singlet on the bottom bond, and then you have a spin that is polarized with the field on the opposite side. So clearly, if you have antiferromagnetic interactions, right, along these black bonds, right, the spins want to avoid each other, right, because they are fully polarized by the magnetic field, so they don't want to be together. Okay, you don't want to have two spins, being near neighbors, because then you have to play this exchange energy, right? Here. So they try to avoid each other, and the best way of avoiding each other is by putting a singlet in between, right? And therefore you automatically get a ferroelectric state. So this is the intuition. This is the way you start, right? And you do all the calculations. But it's very easy to see that having antiferromagnetic interactions along the black bonds, you effectively produce a ferroelectric interaction between the electric dipole, right? And via this mechanism, again, you can switch on electric polarization with a magnetic field. So to conclude, magnetic or exchange coupling between primers leads to spin orbital physics, right? You don't need to start with multi-orbital models. Even with single orbital models, you can end up with spin orbital physics. The charge degrees of freedom are strongly coupled to the spin degrees of freedom, right? As you saw in all these models. And this really leads to very interesting magnetoelectric effects, in particular the one that I illustrated today, is that by applying a magnetic field, it is possible to switch on the electric polarization via spin flop via first order transition. And something interesting also is that this ferroelectric state has quasi-gapless excitations. If you look, of course, these higher order corrections in 1/s, these quantum fluctuations will induce a small gap. That's the reason why I said that was a pseudo or small. And that gap can be very small, meaning that one can observe these purely orbital excitations, right, that correspond indeed to waves of electric dipoles. Probably indirectly, it's easy to see them directly. I don't know how easy it is to measure these excitations. So, this concludes the two lectures. Basically, you can see that in the first one, we saw what are the elementary bricks to build this type of models. I show you the example of one particular case, which is a triangular lattice of triangles, but I'm sure you can think of many other examples. So thank you very much for your attention.
Yes, I have a sort of double question. First, I would imagine that unless you have an easy access magnetic anisotropy, you wouldn't have the three sublattices closing as an umbrella in an external field, but rather you would have a planar configuration going through 1/3 magnetization plateau. At least that would be for higher spins. I suspect for spin 1/2 also.
Let me answer. Well, do you want me to answer that?
Yes, yes, yes.
Okay. That's the reason why I included J double prime. I didn't emphasize it because this goes for experts. If you have, once you have this interaction, right, between the planes,
The stacked triangular lattice wouldn't change.
the stacked triangular lattice with antiferromagnetic interaction along the vertical chain will stabilize the umbrella.
Okay.
So I know what you're talking about, but you know, so it is true for a two-dimensional case. Actually, this Heisenberg degenerate umbrella and the Y, you know, this coplanar phase, right? But when you put the 3D coupling, you remove that degeneracy and then.
It's not degenerate. The planar phase is chosen by the quantum fluctuations.
It is chosen by the quantum fluctuations. I mean, and yeah, something else. You know, probably what you have in mind is 1/s expansion plus fluctuations. Then, you know, something that is even more accurate, you know, for the high field region is to do dilute gas, right? When you do that and you put this coupling along the Z direction, you get that.
And a related question is whether you can get somehow anti-ferroelectric coupling in the planes and get a polarization plateau in an electric field.
Oh, that's a good point. Probably yes. Right.
Very interesting.
Yeah, that's interesting. I mean, yeah, because this is XY, right?
Yeah.
So probably you can. Yes, that's an interesting observation.
Much simpler question on that slide. You're trying to give us an intuition why the spin model gives you the electric polarization pattern on the left, but it seems as though my electric polarizations on the right are polarized vertically.
Yeah.
Whereas you said if you include the quantum fluctuations, the electric polarizations like to point along the triangular directions. Did I misunderstand that?
No, right, yeah, so I chose one particular ground state, right?
Right.
But you can also have the singlets here, and then we point in this way.
Right, but they seem to point at 30 degrees away from what I thought they were. No?
No, I mean, actually, when you put the quantum fluctuations, what you get is these directions, right? And also this direction.
Ah, I see, okay.
You
I
get
misunderstood.
this
All right, thanks.
yeah, degeneracy.
In zero field, I mean, you couple this, I mean, you advertise a 120-degree structure.
Yes.
But I mean, we couple two subsets of spin 1/2 degrees of freedom in a frustrated fashion. So how sure are you that this configuration survives quantum fluctuations?
No, that's a good point. I mean, this is just, you know, the mean field solution. You know, what I'm sure of is that you will not get a ferroelectric state, right? You will get a state that has zero net polarization. But you're right. I mean, this is just a mean field solution, and one has to probably, you know, see how stable. I mean, it is locally stable. That's for sure. You know, when you do the spin wave analysis.
Spin waves are stable.
Yeah, no, right. Spin waves are stable indeed. If that is the question. If the question is if this is a rigorous demonstration that, you know, you have this 120 degree direction, the answer is
But we don't have a rigorous solution for the spin model.
no, but yeah, no, it is locally stable, and you know you get exactly the same type of degeneracy. So at the classical level, again, this state can be pointing in any direction, right? And then you know that degeneracy is removed.
If I understand correctly, you had a 6-fold degeneracy, so it would be like a 6-state clock model. If it was possible to realize then the 2D version of that, which I'm not sure, would you then expect the Kosterlitz-Hauss transition?
Right, and for T equals 6, you would have two transitions.
Two transitions, but one of them would be Kosterlitz-Hauss.
At higher temperatures and
Yeah.
icing. Yeah, right. Yeah.
You would expect that.
Yeah, right. For a 2D realization of this thing, that is probably.
you know, I don't know how easy it is to find a 2D enough compound, but yeah, we are not fully free.
Okay.
Simple question.
Is there real materials correspond to your model?
Thank you for that. Now, right. No, right, as I was saying, you know, the candidates, the typical candidates are organic materials, you know, that contain primers. You know, these papers typically appear in the journals of chemistry. But, you know, this is one example. I'm showing this one just because, you know, in the Magnet lab, they measure the dielectric constant. These are chromium primers, right? They have spin 1 instead of spin a half. So it's not exactly, you know, an example of what I was describing because I was considering that it has spin a half. But basically, if so for spin 1 you have different multiples, right? You have the spin a half, ground state. Sorry, this is spin 3. So you have different multiples, and what you can see indeed is that with a magnetic field, right, you can induce transitions between multiples, right? For instance, you know, from the 1/2 tablet to the next multiplet, so you will have a step in the magnetization. And simultaneously, if you measure the dielectric constant, you see that there is a change in the dielectric constant, meaning that there is indeed a contribution, right, to the dipole moment that comes from this kind of, and it is measured. So the next step, of course, is, you know, to start, you know, so not in this particular compound, but there are many other ones like this one, to include these couplings, right, between the trimers, close to the G, double prime, that I was mentioning before, and then, you know, try to stand. But there are compounds. This is not safe.
This looks like a mechanization platform.
Yes, because, you know, if you have a tablet, right, as soon as you apply a magnetic field, then you will have, you know, immediately one plateau, and then, you know, like, your question, Daniel, is, I don't know, I mean, the best I can for you right now is if you project, I mean, when you write down these spin operators, right, the project spin operators, here, right, S1, S2, and S3, basically it's at this level that you only get X and Y components of the pseudo spin. Right? And the reason, you know, the symmetry reason for your question is that this is a spin. It has to be all in the plane reversal, right? So I cannot put tau z here because tau z times S will give me that is. So basically, because of SU2 invariant, this S has to be proportional to this vector S. And here tau z cannot appear because tau z is all under time reversal. So then, you know, I will get something that is even at the time reversal. Is it clear?
What about the Lattice interaction?
If you have a DM interaction, the answer is yes, of course. The type of term that you will have in this Hamiltonian is tau z S.
For further questions to be asked in the coffee break, and we think it's again.